about graphical criteria for the inequality constraints in directed acyclic graphs with hidden variables.
Okay. Hello everyone, I am Beata. I'm currently a PhD student at ICTQT in science and I work on quantum foundations. So I would like to start with thanking the organizers of this workshop because as someone who's interested in both quantum foundations and statistical causal models, I must say that I really enjoyed the past few days. So thank you for giving me the opportunity to be here. So today I will talk about some work that I did while I was at the Perimeter Institute for Theoretical Physics. As you can see, it's a joint work with Noam Finkelstein, who was actually giving a talk yesterday, and I'm sure you will see some similarities between what he was talking about and like some of the results that I will show today. It's also a joint work with Eli and Ilaya, who are here with us today, and with Rob Speckens, who is with us online. Okay, so since I know that we have a lot of quantum people here as well, I want to start with some important definitions just to make sure that everyone's on the same page. Okay, so I will be talking about directed acyclic graphs, and in DAGs we have three types of structures that occur. So we have forks, colliders, and we have chains. And I would like to introduce an idea of a path being either closed or open, depending on a conditioning set. So we will say that forks and chains are open if we do not condition on Z, or you can see that Z is like this node in a fork or this one in a chain, and we will say that they are closed otherwise. In a case of colliders, we will say that they are open if we do condition on Z or its descendants, and they are closed otherwise. So where are we talking about a path being open or closed? What we do is we consider all contiguous triples along that path, and we want to see whether they are open and closed under the conditioning set. And this definition now allows me to introduce D-separation. So let A, B, and C be sets of variables in a DAG. We say that A and B are D-separated by C if all paths between A and B are closed after conditioning on C. Okay, and I will denote it as here. So what is the intuition behind this definition? Something that we already heard about during this conference is that every time we have a D-separation relation in a DAG, it implies a conditional independence constraint in the data distribution compatible with this DAG. So if A and B are D-separated by C in the DAG, then A and B are conditionally independent given C, okay, in the related distribution. Okay. One more definition that I want to introduce is E-separation. So when I'm saying that a node can be deleted from a graph, I mean removing the node and all its ingoing and outgoing edges. And now we can say that A, B, and if we have variables A, B, C, and D in a DAG, A and B are E-separated by C after deletion of D if A and B are D-separated by C after deletion of every variable in D. Okay, so I'll denote it as here. And now, what is the intuition behind this definition? So you see that it's related to the separation, but it's slightly different because now I introduce this idea of removing a node from a graph, right? So in this case, I'll say that the set of variables D that we are removing are bottlenecks between A and B conditional on C. Because if you focus on this definition, you will see that D must be any set of variables such that it contains at least one node from every path that is open between A and B after we condition on C. Okay, so then when we remove D from the graph, this clause will be now closed and we will have the related D-separation relation. Okay, so in other words, we can say that when D is a bottleneck, what I mean is that all information shared between A and B, conditional on C, must flow through D. Okay, great. So now that we have these definitions, we can talk a little bit more about equality constraints implied by DAGs. So this is the idea that we are already familiar with. When we have a DAG, we can read off some information from it, and we know that it will imply some constraints on a probability distribution that is compatible with this DAG. So one that we already heard about, even at the previous presentation, is just the Markov condition. So if we have a DAG G with some variables V, they must decompose as follows, right? So if we have a DAG, if we have some data, if we have some probability distribution, and all the variables in our DAG are observed variables, we can actually test, this condition and see if the probability distribution is compatible with a DAG. Another one that I already mentioned is the one connected to d-separation. So if we are given a DAG, and we can, read off the d-separation relations from it, we know that we should expect the corresponding conditional independence relations in the distribution that corresponds to this DAG, okay? Conditional independence relations are also equality constraints. And moreover, we have this feature that if we want to test them, we need the variables in the set in the conditioning set to be observed. Okay, because what happens if you have some unobserved variables in a DAG? If you have unobserved variables here, we won't be able to test the corresponding conditional independence constraints, right? And this is something that I want to focus on today. I want to ask how to study causal models with unobserved variables. And there are some approaches to this problem. One is called quantifier elimination algorithm. I don't really want to go into detail here, but basically what we can do is that if we have a DAG with some set of variables, we can take all the constraints that we have on the observed and unobserved variables, run the quantifier elimination algorithm, and try to eliminate the unobserved variables from our constraints. Because at the end of the day, even if we have a DAG with unobserved variables, what we want is a constraint or a set of constraints on the observed data distribution, right? So we want to eliminate the unobserved variables from our constraints. And we can do it in principle with quantifier elimination algorithm. We will get some inequality constraints from it. The problem here is that it's numerically not always tractable. So for example, if we have a DAG of like 6 or 7 variables, including the hidden ones, it becomes challenging to get the set of inequality constraints. Okay, it was also shown by Evans that every time we have an e-separation relation like this, there will be a constraint on the observed data distribution. Okay, so whenever we have d-separation, we have an equality constraint. Whenever we have e-separation, we also have some constraint, but this result was not really constructive in a way that it didn't show how to get the specific constraint. So when we have d-separation, we know that we have conditional independence. And now the question is, when we have e-separation, what is the constraint that we can get on the data distribution from this e-separation relation? And this is the question that I will answer today. But before I go to the main, formal theorem, I just want to present you one example that I think gives a very nice, intuitive way of understanding the type of constraints that I will be talking about today. Okay, so let's consider this example. Let's say that we have Amy, Bob, and Cathy, and Amy wants to send some information to Cathy, but she can only do it through Bob. Now, if Bob only ever sends the same one message to Cathy, there is no way that Cathy will learn something about Amy's node, right? So how do we quantify this capacity of Bob being able to send some information from Amy to Cathy? We can do it with entropy. So in this case, when Bob only sends the same node, we say that Bob's nodes have 0 entropy, where the entropy of a random variable is defined like this, and it's minimized by a point distribution. So this is what's happening here. Okay, so what happens if the entropy of Bob's nodes increases? Now there is some potential for Cathy to learn something about Amy's node, right? But there are no guarantees. Bob just can be sending Cathy anything. So already from here, you get a flavor that we won't have an equality constraint, but we'll have an inequality constraint, because the fact that Bob's node, the entropy of Bob's node increased doesn't really mean that Cathy will actually, learn something about Amy's node, okay? Because you still don't know what is the information that he's sending. So we can quantify this example using mutual entropy, which is defined like this. And here we would say that the information shared between Amy and Cathy is bounded from above by entropy of Bob's nodes. Okay, so we have this intuition here. Okay, so I just wanted to show you this example. Of course, it's a very simple one. And here we can say that Bob is a bottleneck, okay, because all the information coming from Amy to Cathy must go through Bob. And we see that the entropy of the bottleneck is somehow connected to the mutual information between, the nodes in our graph, between which we want to pass the information, okay? So formally, and I will not show the formal proof here, but if anyone is interested in it, just let me know. We will have this theorem, okay? So we'll be talking about discrete variables. And let's say that you have this E-separation relation in DAG. So you observe that A and B are E-separated, a condition on C upon the deletion of D. And in addition, no element of C is a descendant of any in D. Then we have the following constraints, okay? So this is exactly what we wanted to do. We are given, or we observe an E-separation relation, and from it, we have a way of constraining, of putting together, constraints on the variables of interest. If in addition, no element of A is a descendant of any of D, then we can get stronger constraints, which are given here. So as you can see, the difference here is that here we are also conditioning on D, so we are also conditioning on the bottleneck, while here D goes here. So we have the mutual information between A and B and D. Okay, so let me illustrate how this theorem works in an example. And at the same time, I will answer a question that might be in your heads right now. And is that I was talking about quantifier elimination technique previously, right? So you might ask, if we have this theorem now, that obviously seems easier, right? We just have a DAG, we read the separation relation, and from it we have an inequality constraint. How does it relate to results that we can get when we just use quantifier elimination? Okay, so let's start with this example. Say that we have the following DAG. So as you can see, we have like two confounders here, and this is just a chain. So if you want to apply the theorem, the first thing that we need to do is to identify the bottlenecks or identify the separation relations. So for example, let's say that we are interested in mutual information between A and Z. Then, of course, all information must pass through X and Y. And this can be also formalized by an E-separation statement. And from this, we will get the following inequality constraints. Okay, so you can see that I use the stronger version of the theorem here. The conditioning set is just an empty set here. And we have the mutual information between A and Y and Z in this case. And here we're talking, in the second case, we're talking about mutual information between A and Y. A and Z, sorry. Okay, so we have these two inequality constraints, and it turns out that in this particular example, we recover all Shannon type entropic inequality constraints implied by the graph. So these are the same constraints that you will get, just using quantifier elimination technique, which is great because obviously this way is like a way faster way of getting the constraints. On the other hand, we can also look at a different example. So now you see that instead of having an edge here, we have this edge, and we still have two confounders. We can identify what are the separation relations here, and we will observe these two inequality constraints. Now, if you were to run a quantifier elimination algorithm, you'll get this constraint as well. So you can see that the first one that we get here can be strengthened to this form. So the difference here is that here we have the entropy of X, and here we are additionally conditioned as the entropy of X condition on Y. So this is a stronger constraint than this one. Okay, so we see that this is not always the case that we will get all inequality constraints using this technique, but it's still very useful, especially if we have DAGs with multiple variables and it would be hard to run the quantifier elimination in the first place. Okay, so we do have some related results in the paper, and I don't want to go like too much into details when it comes to them and like give too many examples because we also don't have that much time, but I will mention them. So just if you have any questions, we can discuss it during the questions session or maybe later. So first related result is that it is possible to relate our inequality constraints to equality constraints. For example, to the one related to the separation, the conditional independence ones, but also to Verma constraints. And it is done through this proposition that if A is d-separated from B by the set CD, then A is also E separated from B by C upon deleting D. So every time we have a D separation relation, we'll also have a corresponding E separation relation. But this doesn't work the other way around. Okay. Okay, so now let me talk about some applications of this result. The first one is about causal discovery. So let's say that we observe the data distribution. Okay, so we have a distribution over the observed variables here. So all the y's, and we know, or our causal hypothesis is that the observed data distribution is described by one of these DAGs. And they're very similar, except that this one contains a directed edge from y1 to y4. Okay, so the question that we're asking here is, we have a data distribution. We know that this structure holds, and in addition, we want to know whether there is a direct causal effect from y1 to y4. Okay, so if we have a probability distribution over the observed variables, the first thing that we do is we test the equality constraints, right? But in this case, it turns out that the two DAGs share the conditional independence constraints. So thus, by using the equality constraints, it's impossible to distinguish between the two. But what we can do, we can use our inequality constraints. So we can write down the separation relations that hold in a graph. And yeah, let me go from the bottom here. You see that this one is shared between the two, so I'll not focus on it. But for example, let's look at this one. So we have that y1 and y2. So these two are E separated from y4 if we remove this node from a graph, right? Makes sense. But now, if you go to this example, even if we remove this node from a graph, we still have this edge here. So this is separation relation will no longer hold. So we have it here, but it does not hold for this DAG. And now we have one more separation relation. And the thing is that this one is stronger than this one, okay? So you can see that they're similar, but in here we have y4, and here we only have y3. And it's also because of this edge that this constraint is stronger than this one. So I didn't write down the resulting inequality constraints here, but for every separation relation, we are able to use the theorem to write the inequality constraints. And then you can use these inequality constraints to reason about the causal structure. Right. Another example that I have here concerns latent variables. So one more related result that we had is that, remember I said when we have hidden variables in the conditioning set, we cannot really test the equality constraints, right? But what we showed is that if you have some additional information about the hidden variable, for example, its cardinality, or maybe its entropy, then it's still possible to get inequality constraints on the observed variables that somehow use this information that you have about the latent variable. So let's say that we have the following situation. We observe this data distribution, and our task is to decide between these two causal structures. So we do know that there's a hidden common cause, but what we don't know, and we want to find out whether there also exists a direct causal influence from X on Y. And let's say that we can make the following assumption, that the cardinality of the hidden common cause is equal to 3. And this is very often, I feel, a valid assumption, because even though we cannot always, observe the confounder, sometimes you can identify what it is, and then we know also what is the cardinality, right? Okay, so we had the following proposition in the paper, that if A and B are D-separated by C and U, where here U is the set of unobserved variables, then the following inequality holds, okay? So you can see that on this side, we only have the observed variables, and on this side, we have U, the unobserved variable, but it's only the cardinality of U that appears in the inequality. Okay, so for this specific example, here we have 3. Again, the conditioning set here is just an empty set. So we can compute this expression, and we will get something that's slightly larger than 3. Okay, so looking at this again, here U D-separates X and Y, but here it is not the case, right? So if we observe this probability distribution, we observe that this inequality is violated, and we can conclude that, it's impossible to explain in a model where U D-separates X and Y. So it's impossible to explain in this model. Therefore, we have a direct causal influence from X to y. Now, I think that this proposition is very interesting because you can also kind of use it the other way around. If you do not know anything about the cardinality of the common cause, but you want to find out something about the cardinality of the common cause. So let's say that we're still observing the same data, but now we are convinced that there is no direct causal influence of x and y. So this is just our causal structure. And what we want to do is we want to bound the cardinality of the hidden variable. Then we can use the same proposition again. And what we now see is that this cardinality, in order, so this graph explains this observed data, must be at least equal to 4. Okay. One more application that we find for our theorem regards quantifying causal influence. So throughout the past 2 days, we heard a little bit about the average causal effect, and this is a very standard way of a very traditional approach for quantifying causal effect. So it's defined like this, and usually here we talk about some treatment and some outcome, and we usually talk about binary treatment. So here x is the treatment; it can take these 2 values, okay, and this is how we define the average causal effect. And of course, this definition is shown to be useful in multiple cases, but there are also some problems that can occur when you use it. For example, you could find a very specific scenario in which every treatment will affect the outcome, but when you actually compute the average causal effect, it will be equal to 0. So the outcomes, or like these terms, will somehow cancel out. So you'll have the average causal effect of 0, although there actually exists a causal effect of the treatment on the outcome. So this is one thing. And another thing is that you see it's defined for a binary treatment, right? So we could somehow extend it to the case where x has higher cardinality than 2. But like originally, the intuitive way of understanding the average causal effect is exactly this one for binary treatment. So our response to this was that, well, we can use our theorem to help and our intuition that we developed with separation to define a new way of quantifying causal influence that maybe can be used alongside the average causal effect to give us some additional information about strength of a causal arrow. Okay, we called it minimal mediary entropy, MME, and it works as follows. Let's say that we are interested in the strength or this arrow. So it's a directed causal effect of x on y, okay? And we know that we have this DAG. Now, it goes as follows. What we need to do is to introduce 2 additional latent variables, w and u, such that the w mediates the whole causal effect along this path, okay? So instead of having this one edge here, now we have that w mediates the causal effect of x on y. And of course, we can always allow for this hidden common cause for w and y because it won't change the structure overall. Okay, so now that we have this new DAG, the question that we can ask is, what is the entropy of w such that we can recover this situation here? And now this definition very much, reflects the fact about, like, maybe not bottlenecks, but the idea of conveying information along a path and how the entropy of variable along the path is connected to how much information we can actually transfer. So we define the minimum mediary entropy to be the smallest entropy of w, where w is the variable that we inserted, over all structural equation models reproducing the observed data distribution over the modified DAG, so over this one, in which w has finite cardinality. Okay, and I won't really give you any examples here. And just from looking at the definition, you could ask, okay, how do I, optimize over all structural equation models? But we can actually show that in some cases, our theorem would be useful to just give a bound on the entropy of w. Okay, so in particular, if we observe this E-separation relation, we're here dilating w and some set d. So you can see that w here would be just like, a part of the whole bottleneck, the set that we call the bottleneck. Then we will be able to put a bound on MME from x to y. That depends on the mutual information. MD entropy. So there is one bound. There are also some trivial bounds that we can put. And of course, although it would be hard to optimize over all structural equations, we can look into like some specific examples and try to, tighten the bounds that we already have. Okay, so now I want to move to a different result that also regards equality constraints, but from this part of the presentation, I think the most important take-home message is that E-separation relations imply entropic inequality constraints. Okay, so every time we have an E-separation relation, we can just give the, the corresponding entropic inequality constraint that constrains the probability distribution. Okay. So now I will be still talking about inequality constraints, but I want to focus on this particular case of restricted cardinality. So where we have an unobserved variable, but we know its cardinality. And in order to present one more result, I need to introduce one more definition, and is that if P is a non-negative matrix, the non-negative rank of P is the smallest number R, such that P can be decomposed like this. Okay, so we have this non-negative matrix, and we are looking for this kind of decomposition, where this is one of these would be a row vector, one is a column vector, but you can see that the number of terms in the decomposition is R, and what we want to do is we want to minimize this R. Okay, and this is what people call a non-negative rank. Now, why is it interesting? Because it can be interpreted as a measure of dependence. So it's a trivial observation that we can represent the probability distribution as a non-negative matrix, right? And now if it's a probability distribution over X and X and Y are independent, then of course you'll have this factorization. And in this case, the non-negative rank of this matrix here is equal to 1. But now, as the correlation between X and Y increases, so does the non-negative rank for the distribution, okay? So it can be treated as this measure of dependence. And now maybe it sounds familiar to you with respect to something else that we can treat as a measure of dependence, and it has to do with conditional independence. Okay, so if we have X and Y and they are conditionally independent given some Z, then you can write down the following equation. No? Okay, if X and Y are actually independent and we do not need, Z to make them conditionally independent, R is just equal to 1, right? And we'll just have this term here. And again, the more correlation we have between X and Y, the higher must be the cardinality of Z in order to, explain this conditional independence. So I hope you can see this correspondence here, that here, as the non-negative rank increases, X and Y can have stronger correlations. And here is the same, but with the cardinality of Z. And it can actually be shown that these two numbers, so the non-negative rank and this cardinality of Z, correspond to each other. But the way I want to show you the result is I want to still, talk about the graphical criteria. So again, we can connect conditional independence to D-separation, and we can make through this slide the connection between D-separation and non-negative rank. And it goes as follows. So the non-negative rank of the matrix that describes the probability distribution over variables X and Y constitutes a lower bound for the cardinality of a variable Z that D-separates X and Y. Okay, so we have this inequality constraint that again can be used if if we have unobserved variables. So in here, X and Y can be observed, must be observed, and Z could be an unobserved variable. It's a D-separating set, okay, so it's something that we condition on, but since we know its cardinality, we can use this inequality constraint to reason about the causal structure. Okay, so we could use it for causal discovery. So there is this one example that I showed, before with relation to this other inequality constraint, where we want to, see whether there is a direct causal influence from X to Y. So I don't want to go through this example again, but I hope you can see that the flavor of this inequality is very similar to the flavor, with the inequality with, again, the cardinality of the hidden variable. So I could just go over the same example and use this cardinality instead and see, how I can reason about the causal structures. So let me not do that and let me focus on a different example that I also find very interesting. and it's about distribution generation. So distribution generation is a problem that's studied in communication theory, and it goes as follows. Suppose that we have two parties, Alice and Bob, and they're responsible for generating random variables. So Alice generates X, Bob generates Y, and they want to generate it in such a way that they have a pre-specified joint probability distribution. Okay, so there are different ways in which they can generate it. And now two different questions that people ask. Oh, sorry, but we have a bird here. Okay. That's nice. Okay, sorry. Two questions that people ask in this situation goes as follows. So the first one is how much information must be communicated to generate this probability distribution? And here I'm talking about one-way communication. So for example, how many bits must Alice send to Bob for them to be able to generate this pre-specified probability distribution? And in the literature, this number is referred to as randomized communication complexity. And this is a pretty well-studied problem. And this is the result. So this is the number of bits that they need to communicate to generate this probability distribution. Now, a different question that you can ask is how much information must be shared between Alice and Bob for them to generate this probability distribution. Again, pretty well-studied problem. It's referred to as randomized correlation complexity and is given by the same number, actually. And now, I think the nice feature of this problem is that if you look at the literature, it's a well-studied problem, but people usually consider these two questions as two very different questions that are not connected to each other at all. And the way that they get these results is maybe not very complicated, but it requires a bunch of algebraic manipulations. While with the result that I showed you on the previous slide, you can actually see a very close connection between these two questions, and you can just answer the question straight away. So what you need to do is you just need to take a causal approach, okay? So what this question is really asking is that we have Alice, we have Bob, and now we have some mediator, and we want to know what is the cardinality, like the minimum cardinality of this mediator, such that, you know, X and Y can have some pre-specified probability distribution. And now, if we look at this question, what we really have is just a common cause. And the question that we are asking is, what is the cardinality of this common cause, you know, such that X and Y, we have this pre-specified probability distribution. And in both of these graphs, of course, Z de-separates X and Y, okay? So it turns out that this is actually you know, these two questions are very much related to each other, and we can use the corollary to get the answer right away. So the result was that the cardinality of Z must be bounded by the non-negative rank, and you know, we just put the logarithm here for it to correspond to how the question was originally asked. So I think that this causal approach gives you a very nice perspective on this problem and shows that it really can be simplified when we look at it this way. Okay, and now one more connection that we can do with this problem is to ask about the quantum generalization. Okay, so in the previous slide, we had access to classical information. So that was a classical variable, but now we can ask, you know, we still have the same task, and we're asking what is the minimal dimension of a quantum state, okay, that Alice and Bob, you know, either communicate, so they have a quantum channel, and like the question is, what is the dimension of the quantum state sent from Alice to Bob if they want to generate this probability distribution, or what is the minimal dimension of the quantum state that they share, you know, and somehow use this information from this quantum state to generate this probability distribution. And I just want to make it clear that this is a problem that was also studied in the literature, and we didn't contribute to the quantum generalization, but I still want to point it out here because I think it's a very interesting connection to our result in the classical case. Okay, so to answer this question, I need to introduce one last definition, and this is a positive semi-definite rank of a negative matrix. It's again, what we are interested in doing is just we have some matrix and we want to make some particular decomposition, okay? And a Psd-rank is just basically minimizing R, where R corresponds to the dimension of these matrices. I don't think it has, as nice of a interpretation as a non-negative rank, but we just need it as a definition here, because what people showed is that the dimension, so D here states for this dimension of the quantum state, is bounded by the Psd-rank of this probability distribution. So you can see that the resemblance that in our result here on this side, we had a cardinality of a classical variable. Now we have a dimension of the quantum state. And in our result, we had a non-negative rank here, but now we have a Psd rank. And something that's a nice feature, but not very surprising, is that in principle, Psd rank can be smaller than the non-negative rank. So if you want to generate a probability distribution, the dimension of the quantum state that we need in order to do it can be in principle lower, and it can be, a very big difference, a significant difference than the cardinality of a classical variable that we would need in order to generate this probability distribution. So I think that this is just a very nice connection between the two problems. And of course, the classical case is definitely, well studied, because we had this whole connection to d-separation, while here, in the quantum case, you're just talking about sharing a quantum state or communicating a quantum state. So we don't have, a very nice result that we could apply to any kind of quantum causal structure that we could use. But still, I think this connection was important to point out. And yeah, that's all I wanted to say today. So thank you for your attention.
Great. So thank you for the very nice talk. And there are several questions back there. So I'll start at the back this time.
Thank you. Very nice talk. Just one question. You had a result early on where you said E-separation, the inequalities gave you everything. And could you say a couple of words about how the proof for that works?
Oh, so it's just if you were to run the quantifier elimination technique, it's one of the DAGs that were studied in the paper when they derived the full set of inequalities. And just by comparison, you can see that you get the same with E-separation. So.
Yeah, thanks for the very nice talk. I was wondering if you could say a bit about, related to the part where you discussed causal discovery, what kind of faithfulness type assumption might be relevant in that setting? So if, for example, when you were comparing A and B were confounded by U versus the one where they were confounded and there was also an edge. So is there some sort of underlying assumption that you have thought about that would say that that edge is real, that it really, that the inequality binds in some sense?
Mm-hmm. So we didn't really consider that, but of course, you need to imply the faithfulness principle, because of course, it would be possible that we have some fine tuning, right? And this is why we do not observe the edge. But I cannot really say anything more about the particular assumption.
Are all the inequalities captured by entropic inequality? Are there inequalities that are not in the form of
entropic inequalities? But okay, so you're not asking about just implied by the in-separation, but in principle.
Right, there might be inequalities. The
Yes.
model might imply some inequality, but it's not in the form of entropic inequality. Is that possible?
Yes, of course. But on the other hand, it's also possible, for example, we have Bell inequalities, right? That are not captured in terms of entropies. But on the other hand, I believe that you can write down an entropic version of Bell inequalities. So there is some correspondence. But the answer to your question is yes.
Do you know what is the gap, or what type of inequalities are captured by entropic type? What's missing? Why it's missing?
That's an interesting question. So one thing that I can say that, for sure, from the example that we have here, entropies are good for capturing this idea of a bottleneck. So this is why they correspond to separation relations. But also when you use quantifier elimination technique, you're looking for this inequalities in the Shannon cone, right? So you also get entropic inequalities. I'm sorry, I'm looking at Ellie here, but I think he might get a better sense of that as well. So. Yeah, so there's definitely some intuition behind it, but not a full well-defined intuition that would tell you why I do this. Like Entropic inequality constraints and the other inequality constraints are not in terms of entropy.
Okay, I have a question. It's in your example, you have this 2 to the power 1.549. Could you just say a little bit how you get that number? I want to understand this more concretely.
Okay. Yes, of course. Okay, let me just find the example. Okay, so you're talking about this one, right? Yes. Okay, so is your question how do we get this result, or just how do we compute? Okay, so it's just we just need to compute the mutual information, and since we are giving the observed data, mutual information is just you know, given in terms of entropies of x and y and the entropy of x and y, which are well defined. So we can just like compute the entropies and then plug it into the definition. And
in that table, so say for the first 1.002, what does it mean? It's
yeah, sorry. So this is just like observed data as such that these are the probability distributions. So you can see that like if you sum over the right ones, yeah. But it's just we are assuming that x has cardinality 4, so it can take these 4 values, and the same for y. And for example, that the probability distribution of getting this result and this result is equal to this.
Okay, great, thank you.
Okay, I think we have time for one more question, and then it's time for the break. But Beata is here, so we can ask some questions.
So just to follow up on that last question, so you're just the assumption is that this is the distribution and it's known perfectly.
Yes.
We're not taking this. So yes. I wondered if you thought about taking into account sampling variability when you're using entropy as a.
Oh. Not really. So to be honest, when we came up with this example, we wanted a particular data that would violate this inequality. So this is like very much fine-tuned to violate this inequality. And I guess your question is, if you don't know this exactly, what is like, of course, we wouldn't be able to estimate it. Well, then I guess it depends. Like, for example, here, this number is very close to this one, right? So if we won't be able, like if we didn't know this exactly, then it is possible that we wouldn't be able to decide between these two structures. But I think if we are using this proposition the other way around, and we are just interested in maybe the order of magnitude, like more or less what U is, we could still kind of get a sense of the cardinality of the hidden variable, even if we didn't know the distribution exactly.
Okay, so I think let's thank Beata again and then move to the break.